Dr. Parchamazad at the University of Laverne, and then I taught there for 3 years, 2002, 2006.
Нет, он,
back
это
to
такое.
And, he's an expert in zeolites. He's been working in zeolite systems for many years. And because to me, he got interested in cold fusion and tried experiments with cold fusion using zeolites. Which one is it? Verne. Okay. This is Dr. Parchamazad, and he actually was went to school first in Iran and did his education there, and he was a professor there. But when the religious people took over, he and his wife went to a meeting in France and never returned. Left his family, left his relatives, some of his relatives there. But he and his wife then came to France and continued education in France, and also did work in Germany on fuel cells, and later came to the University of Laverne. And he's been chairman of the chemistry department there in Laverne. A little bit about zeolites. Zeolites are unusual in there are aluminum, silicon, and oxygen compounds, and they have cavities of different sizes. And you can pick different zeolites, a lot of different zeolites. You can vary the pore sizes and cavities, the size of the cavities here. And the main important thing about zeolites, they have a very strong electric field inside the cavity, inside the pore. And this can cause perturbation of the molecular wave function, and he sees the reactions inside the zeolite are different than what you observe outside the zeolite. He's an organic chemist and did a lot of organic reactions inside zeolites and found the behavior is quite different than what you would see outside the zeolite. And in cold fusion, his work is to get palladium in the zeolite, and we'll get to that in a minute. This is just some examples of some chemical reactions, organic, polymer type reactions that he's done. And a reaction like this will not take place going to this product outside the zeolite, but he could get these things to happen inside the zeolite. And you can get different results than you would get outside. So we put the palladium inside, and their electron transfer reactions can take place in here that are different outside. And he considers in the zeolite framework, it acts as a supermolecule with strong correlated SPD and F electrons. And you can have different size cavities. Here's larger ones, here's smaller ones, so that you can have variations of cavities. My introduction to zeolites was when I was a research chemist at the Navy, and organic chemists would use zeolites to remove water from organic solvents, because water would go in the pores, but the organic solvent would not. You could remove water, for example, and purify the solvent by the use of zeolites. There's another use for zeolites. That's quite a few different uses. Where is the guest molecule? And he can make it what we call quantum dot. He likes this term quantum dot. I don't know if I quite understand it, but and he can do things like he would photo reduction of CO2 to hydrocarbons. He's interested in that inside the zeolite. Also, this he's quite interested in the removal of estrogen from drinking water. It's a contaminant in drinking water because it's used a lot. It gets in the drinking water, and zeolites act to remove this from the drinking water. He's interested in that area. And all this he thinks is because of the very high electric field. It kind of reminds me of the double layer in electrochemistry, where you also have an electric field in the double layer about this magnitude. 0.7 volts per angstrom. And if you do that in volts per meter, that's a very large number. But in angstroms, it's 0.7 volts per angstrom. And so you think of these perturbations and things in the nucleus, in the strong electric fields, you can also, the nucleus also gets affected inside the zeolite. Like the nucleus of a platinum atom, perhaps, inside the zeolite. Now, he finds that some of the rules are not followed inside the zeolite that we find outside when we do chemistry. He does organic chemistry. For example, this reaction, so these two double bonds form a ring of four sides here. You can't get that to go without using light. Heat doesn't work. Forbidden with heat to get that reaction to go. But inside the zeolite, this reaction happens without light. You don't need the light, and this process will take place inside the zeolite. Okay, why did we choose platinum? Well, of course, he became interested in cold fusion. He accepted cold fusion early on. He was open-minded, unlike a lot of people. He was open-minded that plasma bonds were correct. And so he wanted to try this. He wanted to, but he knew you'd have to get the surface very clean. And the way he would do this,